Let's discuss about the structure of atoms. So let's just imagine this is an atom here. Let me make it clearly here. So this is the nucleus, and the nucleus will contain of N for neutrons and P for protons, and also on the outer layers will contain electrons. This is called a stationary object. Electrons are the negative charges, neutrons are neutral charges, and protons are the positive charges. Both electrons and the protons have the same charge. They have the same charge, but they have different symbols. Electrons having the negative symbol and protons having this has zero charge or no charge, negative charge, and the masses go as this. The neutron and the proton both have the mass 1.67 into 10 to the power minus 27 kg. These two are coulombs. So 1.67 into 1.67 to 10 to the power minus 27 kg. They have the same mass, where the electrons almost negative. Moving ahead, the number of electrons, which is equals to number of protons, is also equals to Z, which is the atomic number, and mass number is equals to the atomic number plus the neutron. Technically protons plus neutron. Now in the proper convention, this is how it is written down. I will show you in a minute. For example, we take a substance like helium. Helium, atomic number is on top. I mean, the mass number is on top, atomic number is on the below. Something you can remember is A to Z. A is on top, Z is below. That is the normal convention how it goes. Now, what's the difference between? Let me take a pink. What is the difference between nuclear reactions and chemical reactions? So if you had to actually tell or differentiate this, here are a few points. Chemical reaction is low energy is generated, electron volts, whereas here in nuclear reactions high energy is liberated, which is mega electron volts. Here mass, numbered, and atomic number remain same after the reaction. The electron configuration changes here. There are 2 points. Now, moving ahead, let's talk about isotopes. What are isotopes? So, isotopes are atoms having same atoms of same element having same atomic number. So they have same atomic number, that is D, and different mass number, A. An example of this is hydrogen. Hydrogen has H101. Oh wait, H11, H21, H31. Each of them are named as follows. This is protium, deuterium, and this is tritium. There are two kinds of isotopes. Just to show something. Just to I don't need to eat mutton today. Two kinds of this thing are stable and unstable isotopes. Now let's talk about another thing. It is called iso isobars. This is atoms of different elements which have same mass number A but different atomic number. See, example are Na2311 Mg2311. Something to also note is that 2012. Something to also note is that this one has 11 protons, this one has 12 protons, whereas this thing gets opposite. So neutrons is equals to 12, neutrons is equals to 11. So these are due to this, these are called mirror isobars. Then the next topic is isotons. Atoms having different atomic number V, which is protons, but the same number of neutrons. Example for this is do not confuse with this space 2311 Na with 2411 Mg. So they have the both same number of names, which is they have both tiles connected protons of 11. Don't get confused. The next topic is radioactivity. What is radioactivity? Well, radioactivity is a physical field It is a physical chain. So not to get confused with these two, because these are separate things. There are 23 mgs given, whereas 24 mg. Now what is radioactivity? Radioactivity is a physical change this is this is wrong. So this is a nuclear phenomenon which is the process of spontaneous emissions of alpha and beta particles along with gamma radiations from the nucleus. During their decay. So let me write down the diagram for you, because diagrams are important. Imagine there's a box, or this is the substance. A substance is. From here comes three radiations. Three radiations. One. Okay. This is the negative side. This is the positive side. These are beta rays. These are alpha rays. This is gamma rays. And within a lead box, so there is a lead box, is the substance. And this is the lead box. Lead box, why? Because lead box prevents radiation from coming out. Now as you can see, the alpha rays are a little higher than the beta rays. Let's study about the Now let's study about the properties of these rays. Starting off with the alpha rays. So it is technically kind of equal to doubly ionized helium atom. Doubly ionized helium atom is represented as 4 2He. I'm going to go through the properties in a very brief manner. You have to just go through the book, and I recommend you going to the table provided. Now, here are the few points that you need to remember. Speed is 10 to the power 7 meters per second. Mass is 6.68 into 10 to the power minus 27. Kg. There is, which I just remember. Instead of remembering this, you can just remember the following. What I write down: 4 times the mass of a proton. The next point is charge. Charge is equal to 2 times of a proton, which is equals to 3.2 plus 3.2 into 10 to the power minus 19. Next point is ionizing power. Its ionizing power is maximum, which is 10,000 of gamma rays. Penetrating power, since its ionizing power is the most, its penetrating power will be the least. Okay. Now that alpha rays are done, let's talk about beta rays. Beta rays. These are energetic electrons. You can tell about energetic electron, and if you are a bit confused of that, it is 0 minus 1 e. Fast moving electron or energetic electron is fine. I would recommend you to write fast moving. And the next point is speed. Speed is 2.7 into 10 to the power 8 meters per second. Third point is mass. It is equal to the mass of an electron, which the mass of an electron is, I'll just write down that it's equal to mass of electron. The next point is it is negatively charged, so charge is equals to 1.6 into minus 19 coulomb minus e, so electrons charge. And once that is done, so the ionizing power equals to 100x of gamma. Penetrating power is more than gamma sorry, more than alpha and less than gamma. And last but not the least is the gamma rays. So they are highly energetic electromagnetic radiations. There is no equivalent to this as how much it is, it's just energy. And its speed is 3 into 10 to the power 8 meters per second. That's the speed of air. This has no mass whatsoever, and its ionizing power is least. Penetrating power is most. And that's pretty much it. All of these affect photographic fleets and all that stuff. So that is one thing that you have to remember. Now let's talk about changes in the nucleus in alpha, beta, and in gamma. So in alpha emissions, what happens is, let me write it down. This is the element and atomic number Z. So when the element is reduced, A minus 4, C minus 2, Y plus an alpha particle, which is here helium 4, 2. This is why you have to remember, because they might ask you to write the equations down for this. So one example is, let me give uranium for this. So U23892 gives 23490. If you minus it, you say minus 2 from 90, you get 92, you get 90. 38 minus 4 is 234, and nearby is thorium plus 4 2 E. Now the next one is just first you have to learn about neutron splitting, because you cannot donate the electrons that way, right? The neutron splitting is the following: 0 1 neutron gives 1 1 proton plus 0 minus 1 neutron. Now for example, now once you have got to know this thing, we'll talk about this thing. The pairing nucleus is here, atomic number and a mass numbers are as follows. You get another this thing: A, Z plus 1, you get 0 minus 1 and E here. An example, if I had to give, was carbon, which is 14 and 6. If you were to do that, you'd get nitrogen, which is 14 by 7 plus 0 minus 1 E. So it shifts to the next position in this thing. Now let's talk about gamma radiations. So what happens in gamma radiations is not much of a change happens. except that this, which is in excited state, calm down. That's the only thing that happens here. So no particular change happens here. Gamma radiations. That's it. Now something that you have to note is any given substance will emit only alpha and gamma, or beta and gamma. So there is no this thing for alpha and beta. This is not possible. The next topic is uses of radioactivity in radioisotopes, which is pretty much very easy. I will not go through that. So something else important is to use lead-lined materials, because lead kind of blocks any type of emission. So if you want, I can write that down as a note. Use lead-lined materials as emissions cannot pass through them. Now, in the next section, we have nuclear fission and fusion. So let's do that. Let's start off with nuclear fission and fusion part. Before we go on to something, let's talk about nuclear energy. Some main important stuff you have to remember is that the formula is E is equals to mc delta mc square, where E equals energy, m is equals to mass, c is equals to speed of light. 1 kg of mass equals to 9 into 10 to the power 16 joule slash 2.5 into 10 to the power 10 kilowatt hour. That is important to remember. Whereas 1a dot m dot u is equals to 931 mega electron volts. That is also important. Now let's talk about fission. So this one is the process in which a heavy nucleus splits. So it splits into two lighter nuclei. When bombarded This is a wind bombarded with a slow moving snow neutron, and the amount of energy is around 190 mega electron volts, approximately, that is. So if we were to write down the equation, let me write down the equation. So here are the equations that you have to remember. U is 23592. Again we'll take the same thing because plus 1 slow neutron will give you either 141 barium 56 plus 92 krypton 36 plus 3 again 310 neutron and energy. The same here follows, but the two things mean this thing that we get, the elements that we get are different. So we get lanthanum 57 plus bromine 8535 plus 3 neutrons plus energy. Something to remember here, these two, is that the atoms attain are unstable, so emit beta and gamma. Okay, so the next thing is fusion. Let me write down this thing. It is a process again. This is a process in which two light nuclei, they combine to form a heavy nucleus. So that's the definition there. Now this approximately is 3.3. Okay, while I write the equation. So in total there is 21.6 mega electron volts of energy. Even though this is okay, this is one thing. Why uranium-238 is not used, even though in abundance. It is because it needs fast moving neutron. This is a note here. I forgot in quintessence, so remember that. Two light nuclei combine to form a heavy nucleus. So here are all the equations that we have. This is very less, so it's not actually. Something to remember is that this needs very, so this is somewhere around 21.6 mega electron volts. Is an average. So, and something you need to remember is approximately 10 to the power 7 Kelvin temperature is required here for this to occur. So, if let's talk about equations. So 2 1 hydrogen plus 2 1, so these are deuterium hydrogens. They combine to form a helium atom, which is a helium isotope 1 0 and a neutron, and this gives you 0.33 megamoles. And another one is 3He2 plus 2H1, so helium isotope with deuterium hydrogen will give you 4 the helium and a proton, that is the hydrogen, plus 18.3 megavolts. You can see why it adds up to 21.6 here. This is under high temperature conditions, okay? So something important to note, another thing and last thing in this chapter, important to note is that even though fusion creates less energy, seems to create less energy, to a given amount in a single reaction as a whole for a given mass. Fusion creates more energy than fission, as for a given mass there will be more light nuclei than the heavier ones. That's the end of the chapter, pretty much. Hey, that was pretty fast. Good luck for your exam. Bye.